LQR, fancy acronym. Today, I'm diving into the world of Linear Quadratic Regulator Control, or LQR for short. If you're new to this, don't worry. By the end of this video, you'll have a solid understanding of what LQR control is and why it's such a powerful tool in control systems. So what exactly is LQR control? Simply put, LQR is an optimal control strategy used to regulate the behavior of a dynamic system. It works by minimizing a cost function that balances the system's performance with the effort needed to achieve that performance. This makes LQR incredibly efficient and effective for a wide range of applications. Now let's break it down a bit more. LQR control works by solving a specific type of optimization problem. Imagine you're trying to drive a car along a winding road. You want to stay as close to the center of the road as possible, but you also want to minimize how much you turn the steering wheel. LQR finds the perfect balance between these two objectives. The benefits of using LQR control are clear. It provides optimal performance while keeping control efforts low, making it ideal for systems where energy efficiency is critical. Plus, it's robust and can handle a variety of disturbances and uncertainties. So, what problem are we trying to solve with LQR? In control systems, we often need to manage complex dynamics and ensure stability. The assumptions we make typically include knowing the system's dynamics and having a reliable model. Our goal is to achieve a desired system behavior while minimizing energy usage and ensuring stability. Designing an LQR controller involves several steps. First, we need to model the system dynamics using state space representation. Next, we define the cost function, which usually involves terms for both the state and the control input. Then we solve the Riccati equation to find the optimal gain matrix. Finally, we implement the controller and fine-tune it as necessary. However, designing an LQR controller isn't without challenges. Accurately modeling the system is crucial and can be difficult. Additionally, solving the Riccati equation for complex systems can be computationally intensive. One of the standout features of LQR control is its handling of control effort and disturbance rejection. It efficiently balances control effort, ensuring that we don't use more energy than necessary. LQR also effectively manages disturbances, maintaining system stability even in the presence of external factors. But keep in mind, there's always a trade-off between control effort and disturbance rejection. Achieving perfect disturbance rejection often requires more control effort, so finding the right balance is key. And there you have it. A beginner's guide to linear quadratic regulator control. I hope this helps you grasp the basics of LQR and its significance in control systems. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more insightful content. Until next time, keep exploring the world of control systems.